All right, so this is Sandbox Games using WebAssembly and C++ to make a simple game. My name is Ólafur Waage. This is my face. I'm a senior software developer at TurtleSec AS here in Norway. We are a consulting firm. We also do training, so you can hit us up for that. And you can also yell at me on Twitter at OlafurW. Here's the company that I work for. We do consultancy and trainings and all sorts of fun things, so please look us up. I also was in the gaming industry for 7 years, and I worked in air traffic control for, about 2 years now. So, fun things. Of course, every single talk needs to start with a wonderful quote from a famous philosopher. I must go forward where I have never been, instead of backwards where I have. And this is, of course, Winnie the Pooh. Let's go over first what this talk is and what this talk isn't. This is not a general game development or game design talk. A while ago, I was making games, and I've made some little fun games using WebAssembly. And this talk is basically just the walls I have encountered along the way. This is also not a comprehensive talk about WebAssembly itself. There are other technical talks. This is more a pragmatic talk. So we are here to be pragmatic and learn what this tool has to offer and what problems we can solve. There's one thing with this talk. You might see that I have a little sling. I broke my arm earlier this week, which has kind of hindered me in finishing this talk. So you might see it during the end of the talk where things aren't as polished as I kind of want them to be. So please be nice and bear that in mind when you're watching this talk. It's been tricky to. I'm pretty good now at typing with one hand. So I have this odd setup. The issue is that I also have live demos, so they might be a little slower than normal. But I'm a pretty fast talker as well, so we'll see. Good. Everybody happy? I hope so. Thank you, Fred. So, what is WebAssembly? Like, how can something be neither web nor assembly? Kinda. So, WebAssembly is a binary format. Yeah, we'll go into the details of it. It's originally designed to allow for performant execution of code within browsers. It was announced in 2015. We got a working draft in 2018. We got a W3C recommendation in 2019. And you can think of it as a target output of any language. And in recent times, we actually have tools to execute WebAssembly outside of the web. There's a thing called Wasmer that can, for example, help you with that. But think of it as the target output. Like with regular compilers, we can do binary output or we can do intermediate output. So WebAssembly is just one of those outputs. Many might associate WebAssembly with games. And we're going to use a game in this talk, so I'm not helping. But WebAssembly has much more to offer than just for games. And here are some examples of things you might not have thought of are written with WebAssembly. So you can go and you can find calculator. So someone took the Windows calculator and put it into WebAssembly. If you know Figma, Figma is powered a lot by WebAssembly. It's like a design tool that's been in use a lot recently. Someone made like a Photoshop clone. I don't know. I know that Adobe recently released Photoshop on the web. I don't know how much WebAssembly they use or what they're doing, but at least here's another one. TensorFlow, so you can do some machine learning in WebAssembly. And this is a like DNA sequencing. They sped up their web app by 20 times. So that was a kind of a cool case. So the tool we're going to use is Emscripten, and this is kind of WebAssembly before WebAssembly. Before WebAssembly, we had a thing called asm.js from Mozilla that had similar goals to WebAssembly. It's basically running efficient code on the web. It's a subset of JavaScript, so you would write your low-level code, and it would be turned into JavaScript. And this is where Emscripten came into play. It's based on the LLVM and Clang toolchains, which allows you to target WebAssembly as the binary output. This allows you kind of to get many different outputs. So one of the outputs you get when you compile into WebAssembly is you get the .wasm file. but you also get the .js and .html files, and we'll look into those as well. So let's install Emscripten for those who are playing at home or those who are pausing the video, watching later on. The text editor I'm going to be using is VS Code. I'm using WSL2 running Ubuntu 20.04. And if you want to see the code and want to see spoilers, if you're watching this live, you can go to GitHub, and that's the code we're going to be using. So if you fire up your terminal of choice and you call sudo your favorite package manager, you can install Python 3, CMake, and Git. Then you clone Emscripten core. You go into that folder. Let's do a pull for safe measure. And what you here do is you call Emsdk and you install the latest. This will take a little while, and this will install the latest version on your in your system. You can activate the latest. Why it's doing that? Because you can switch between versions. So you can have the latest and you can have also another version. And there's also an environment variable script. You can source that or put that in your bash RC or something similar. So that should be pretty nice. So now you can do AMCC and version, and you can see that you now have the compiler. You get some fun output. You can also say which EMCC, you can see where it is. So here it's in my EMSDK upstream, and then there it is. Cool. Now we have a compiler. So now what, right? Isn't it the time for the honored tradition of the hello world example? But there are a few more steps that we need to think about before we go into the hello world example. So let's look at them. So I'm going to use a C-like hello world just to show you that you can. So it's a printf hello world with std.io. I call EMCC on hello world. No options, no flags, nothing fancy. And what I get out is two files, aout.js and aout.wasm. All right, good. So this seems pretty simple. I can also, and I can run this. If I have, for example, if I have Node.js, I can run the aout.js file and I will get hello world. But we want something more. So I call EMCC and I do -o and hello world HTML. So this is the first step where we're thinking of something is different, right? And I get the same files, but I also get an HTML file. The JS file and the HTML file are generated, and they're pretty long. And I'll show you at least what the JS file is doing. So yeah, with Node, I can run the JS file. That's fine. But let's start by opening the HTML file. That should be no problem, right? I could just open it in Chrome and that should be fine, right? But here is our first wall. It's a simple wall, but it's a wall. So of course, there's a problem. Browsers don't like opening random files. That's kind of, yeah. There's a thing called cross-origin resource sharing. So by default, browsers don't like loading files from disk. So that's smart, but yeah, we need to get around that. So the browser will load the HTML file, but as we saw, we have other files there on the folder, and most likely that will be blocked. So the best way to solve this is to run a web server that's going to host the files. What I use, so Emscripten has a thing called emrun. There's a tool that comes with Emscripten. It's a simple web server. I wouldn't use it for anything else but for development. But for development, it's pretty good. So when I run emrun on port 8080 and I run it on the hello world HTML file, I'll get this nice little output. So I'll get a canvas, and we'll see why there's a canvas there to draw things into. But I also have a text output, hello world. So great, we're happy. We have a hello world. So let's look at the game that we're going to be making. So I'm not going to be making the game directly here because it's a bit of code, and yeah, that's not kind of not the point. We're going to make, I think, it's a sliding puzzle game. It's similar to the game called Threes and 2048. So let's look at that one. Yeah, let's see how well this live demo thing works here. I can move this over. There we go. And you should see I can zoom in a little bit. I can see the game here. So what I can do is I can tap left, right, and it will merge the little cells. The idea is to get as a big of a merge as possible. There's one difference in this implementation from like if you play this game online, more of a technical thing is this version will fully merge everything. So if it has a merge, and then after the first merge, it can merge again, it will do that, which isn't by design in some of these puzzles. But yeah, so I'm just hitting up, down, left, right, then I can slide those in, and if the numbers are the same, it will merge. And the idea is to get the highest score. So here I have 64. So let's look at the code for this. So if I open up here, our index HTML is pretty simple. I'm just creating a canvas, and I have a game.js, and there's nothing else happening here. And in my game.js, we have the actual game code. And the interesting part is that we have a board, which is just an array. Then we have a bunch of functions, and these are like freestanding functions. And the only thing that they're doing is modifying the state. They're asking, like, can I iterate the board into the next position and next position? We're not going to go into detail on the logic itself. You can look at it on the GitHub if you want to play with it or change it or have fun with it. But the important bits are here. We have a key down event. So I'm pressing the key buttons, and I'm setting some variable of what key I'm pressing. And another important bit is here's the draw function. So I get a context, which is the context for the canvas, and I'm creating a rectangle, just a simple red color, and I'm putting a text in. So these are the two draw things that we're going to do here today. And yeah, and there's a draw function. So every box I'm going to draw, and for the main, I'm getting an animation frame, have some delta updates, and then for every frame I'm calling again. All right, good. We have a lot of things to go through. So let's convert the game into WebAssembly, right? So there are two ways to do this. We can keep the drawing in JavaScript and get the logic in C++, or we can do everything in C++. We're going to look at both and see the walls along the way. So let's take some of these functions that we have in the JavaScript version and just convert them over, right? We can write them in C++, and some of them don't even know about the game state because they're kind of, think of them as pure functions. So here's two of them. One of them is to get random coordinates. This is to spawn a new random box on the tile. And the other one is to ask if you are outbound, is to prevent the boxes from going outside. So you can see that I'm just asking a question about where you are in the array. Great. So here is Emscripten. This is basically, I'm going to include the header file. I have some context per value for the board size. I have the function. I started with the is_outbounds, so I can know if I'm bigger than board size or less than board size, etc. I do extern C, and this is important later for the exporting of the symbols, because I don't want the C++ to mangle the symbols. So that's the only reason why. And the Emscripten keep alive, it might not be necessary for every case. It won't be necessary later on, but I'm putting it here because if it's not used, the compiler might optimize it away, because it's technically never used within this program. And this is the whole program. And then I compile it. We can see a few of the compiling options. So I'm debugging. I also do a debug a G source map. We'll see this later. No entry means that there isn't a main function. I have a standalone wasm, which means that basically this is going to be it. There's just going to be the wasm file. I have the GameLogic CPPP, and I want the HTML file out. All right. I'm not going to use the HTML file here, but I just have some output. All right. So this, we need something then in the JavaScript to load the wasm file. So after I compile this, I have the wasm file. So I have an empty import object because it needs an import object. We'll go into why this will bite us later on. I'm going to call instantiate streaming. I'm going to fetch the wasm file, and when that has finished, then the result is over. I have a results instance, which is the instance of the wasm file. I have exports, which is everything I've exported, and I have is_outbounds is there. So now that's a function in JavaScript, which is then a function in wasm, and I can call that, and that works fine. All right. Good. Great. I mean, it seems we're doing a great job. So let's do the next one, right? We have a get random coordinate. We have a math floor, math random. Seems to be pretty simple. So let's import that one. Oh no, we can't. Or at least there's going to be trouble here. So where we're going now, there's no operating system. So this is a sandbox. So with a pure standalone wasm file, there is no operating system. Nothing like that. You're on your own, kind of, star on that one. So how do we solve that problem, right? So using random, calling timer functions and other like operating system level functionality, it has to come from somewhere. Either you have to implement it in some way, or it has to be provided to you. So thankfully, there is a solution for this. So if you build, like we saw before, we get a .js file in addition to your WASM file. Within that JS file, there's a lot of this functionality given to you, right? But how does that work? Can we do this ourselves? I don't want to depend on this JS file, or I don't know what this JS file is doing, so can we do this ourselves? Okay, so if we look at Emscripten random, this is a thing that's provided by Emscripten. Seems like the thing we need, right? Generates a random number in the range between 0 and 1. This maps to math.random, and math.random is in JavaScript. So this seems like the solution that we want, right? So how do we use it? Okay, let's put that into our code. I have the same setup. I'm only going to focus on one function, so the other is still there somewhere. So I have the same setup. I'm including the Emscripten. I have external C. I have get random coordinate, and then I call this Emscripten random, right? In the JavaScript side, I do this. It's just the same thing I did for the other function. I have an empty import object. I call, in this demo, I called it functions. Doesn't matter much, it's the same file. And I get the random coordinate from the same place in the exports. And I want to console log it. I want to print out this new random number, right? But there's a problem. Type error, WebAssembly instantiate, import, module env. Module is not an object or a function. So what is this? What's happening here? So what's happening is this import object that we're giving to the instantiate streaming, this is kind of the environment or the external world that we're given to the function. So, okay, it seems to want some sort of object or function. So let's put that in. I have an empty env here. The only difference here now is this thing here. Okay, what do I get then? So I have another one. So module environment, function Emscripten random, function import requires a callable. So it's asking for something. And what it's asking for is the Emscripten random function. So even though we were able to call it or use it on the C++ side, it doesn't exist on the JavaScript side. So think of this kind of as linking between those two worlds. And let's look at the text representation. So this is the text representation of the WASM. You can see here, F5, we have our function get random coordinate. So Emscripten is a stack-based VM. So it kind of looks like assembly, kind of looks like some sort of programming language. So we have our function. It's going to return an I32. We have some variables. But here in F9, we're calling env Emscripten random. And the rest is like resolving the stack or resolving the value. And where is this $env coming from? Well, it's up here. So here, someone is saying that there is a func env Emscripten random, which is an import Emscripten random, and it's going to result in a float 32. So we know what this env was. So can we put a function there? So let's try that. So here in the import object, I have env, I have Emscripten random. It's a function, and I call math random. So even though it said like it links to math random, it links to math random in the generated JavaScript file. But if we're providing it for ourselves, it doesn't do that. So now I have an environment, and with the environment, I have an Emscripten random function. And this works. So we're happy now, because what's happening is when you're calling Emscripten random in the C++ side, it is looking for that in the JavaScript side. So we are now providing this functionality over, right? So great. So now we can move over to the rest of the game logic, right? So the board, like we saw before, is an array of arrays of a type I call box. And the rest of the game logic is basically identical. So now what we have, and I'll show you in a bit, we have the gameplay in C++. So the game logic and the updating there is in C++. But we now need to draw the data. So if I go over to here, so now in the second example, I can show you the hello world example is here. Again, if you look at the GitHub, you can see that here. So we have a build, with the builds, and I can run it here. So I can look at that and have fun. So here we have the logic version of it. Okay. So the board is an array of boxes. A box is the same data from the JavaScript side. So where you are in the grid and all that information. There's nothing very fancy about that here. And the rest of the code is the same. So we have our get random coordinate, we have is out of bounds, and all of the functions that were in the JavaScript side are basically identical to the other one. There's a couple of like differences between the languages, but I wrote it in a way where it would be almost one-to-one. So I can go here into the game.js. If I go to like is box mergeable, out of bounds empty, I check for number and delete it of merge. Is box mergeable, it's basically the same. So if you're reading the code and looking at it afterwards, you can see that it's pretty similar. The difference that I have is in the update. The update is coming from the outside. So someone is calling update with the keys that have been pressed, and then I have a bunch of helper functions to get like what is the board size, what is the x coordinate of the box in a certain location. So I have a bunch of help, like a get functions, if you think of it that way. So if I go into, I have a question. I can understand why a random device is not accessible, but I can't see why, for instance, I think the Mersenne twister is available, but the device itself isn't, I think. I haven't gone too deep into the random device one. If you implement it, what is happening is, I think the Mersenne twister is there. I think so. And a lot of these things, like why isn't a thing available, is mostly up to has Emscripten implemented it. So it's not a question of can it be available? It's like have they done something to make it available? So that's kind of the question there. And let me know if you want further clarification. All right. So we have a question. That was great. So in the game.js, now what we're doing is we're fetching the game logic. We have the import object here. You can ignore this one. This was just for a little test for me. I have the import object. I have the same. So the only thing I'm depending on is still the Emscripten random. And now I have all the functions that I need to get the different coordinates and update and all that. So now when I'm pressing a key, it's the same as before. But now when I want to draw it, instead of having the data here, I'm asking for the data from the C++ side, getting the board size, getting the coordinate of every box, getting some information about the number and the width and all that stuff. So now what I can do is I can go into 3, some game logic. I can build it, and I can run it. I should get a browser. Yep, I get a little browser. Let's make that a little bigger. Let's go into inspect. So I have the same game here. I can move the boxes, the same logic here. I don't know how smooth it is on your side. Okay. So now if I go into sources, there's a pretty neat thing that's going to happen is I have the C++ files here. And what I can do is I can debug, like, oh, here's a box update. I would like to break into this. So when I call, when I press a button, now I have a breakpoint here in the C++ file. And I can see the stack, the locals, the call stack from where this was coming from, etc. So I have all the information here, and I can kind of work on this as if it was any other development environment. Okay. No questions here. Good stuff. Yeah, so I can set a breakpoint and have fun with this. Great. And we'll see more of this a bit later. Okay. I also have, if I click on Wasm, I have the Wasm file, and we can see the same thing here. we have the Emscripten random import, and there is no other import. And when you compile these files, and if you want to know if there's anything missing, or if there are any imports that you need, you'll see that there in the imports. We can actually then, some of the names are not very helpful, even though I have debug on. But yeah, you can see that this can get get pretty long. Yeah, here we have get y coordinate. We can also put a breakpoint here, and then I'll get a breakpoint here. So that's kind of, you can map this between. That is kind of neat, right? So the game seems to be working fine. Oh, we are paused. Here we go. The game seems to be working. Everything is happy. All right. So, oh, what do I do with the question? No, I don't do anything with the question. Maybe I do done. There we go. I am an expert. So let's go back to the slides. Okay. Yeah. So we moved everything over, and things seems to be happy. Okay. So where's the data, right? So we can communicate between C++ and JavaScript using primitive types. So just like you saw before, we can send an int over, we can send a float over in that sense. But as soon as we get a bit more complicated, we are kind of in trouble there, right? We can look at the raw data. So let's say that we have a stud vector. There is a way for us to see the raw data of a vector, but a vector in C++ and a list or something in JavaScript, they don't map to each other. They're not the same thing. If you want to then go into the raw data of the vector and use it directly there, sure, you can do that. But yeah, there is a thing called Embind, which can help us passing more complex objects over. But then what you have to do is you have to write these bindings for the type. So here is an example from their tutorial site. You have a my class, and what you're doing is you're giving it a name. You're describing what the constructor looks like. So here we have an int and a string. There's a function called increment x, and then you give it the function pointer to that. There's a property. We have an x, and we have a get and a set. Yeah, and there's like a static function there as well. So you need to do this for your class or your types to be able to convert it back and forth. So that's something that's available, so you can have that. There are even helpers with common objects, so you don't have to write them yourself. So there's something for you to register a vector. So there's going to be like, oh, there's a vector. It's here's the type and here's the name of it. So you can. It's also, I think, for map and all that kind of stuff. So there are ways for you to send things over, but you have to think about that. What's the difference between function and class function? A class function, like we saw here, that's the static one. Function would just be the instance one, and the class function would be the static one. Answer live, done. Great stuff. All right. So what you can do is you can define a shared block of memory that can then be used by either JavaScript or C++. It can even be what they call a shared memory. So these are then basically an array of, think of it as just array of bytes in the JavaScript side, and you can then pass it over. Or it's not passed over, it's given kind of implicitly to the C++ side. I'm not going to go into that one because it's a bit tricky. Whoops, there we go. There's also an option to return a pointer. So one of the primitive types that you are allowed to send over is a pointer, but then you have to know like what is this pointer pointing to, what kind of data is it, what's the layout of it. So this is a territory where you need to be a bit more careful with how each byte is used and represented, and that. And there is a thing on the WebAssembly website. There are assumptions that the sandbox or the running environment has, like that there's the bytes are 8-bit. We are like if they are little endian or big endian, and there's all sorts of these assumptions that you can make and you can be sure of. So yeah, be careful. So thankfully, as I showed before, I wrote the game logic using simple primitives, which was kind of great for the example. So we can finish converting all the functions like I showed you and expose them to the C++, to the JavaScript. Yeah, timing, I showed you that one. So now we basically have everything except the rendering. So now in the version that I showed you here before, I'll go back to this one here. Whoop, nope, wrong screen. Yeah, it's in this tab here. Yeah, sorry. In this version here, what we have is that the game logic is on the C++ side, but the rendering is still on the JavaScript side. So here we still have the fill-rect and the fill style and the text align, all this stuff here with the draw, the canvas and the context. This is still on the JavaScript side. So this main and the timing function is still here. So logic on the C++ side, drawing is on the JavaScript side, okay? So if we go back, this is going well with one hand. So let's move over everything, right? So we've done the first step of, we made the game in JavaScript only, we made the logic in between, and now let's move over everything. So thankfully, Emscripten has great support for what we need right now, because Emscripten has built-in support for SDL, which is a cross-platform library that gives you all sorts of neat things. Among those is a graphical rendering support. Okay. There's also support for SDL2, but it needs to be downloaded. And then, so with the first time you compile with the SDL2, you'll see a download happening. But then after that, it should be cached in your Emscripten folder. What you do is in your compile flags, you add, and you'll see a lot of these when you start using this, you'll see a -s and then something. So those are the flags that are being sent to Emscripten specifically. So we're going to use SDL2, and we're going to also use the TTF, the text, because we want to draw the little text thing there. Okay. And also, since we're going to use SDL2 and other built-in functionality, we're going to use this generated JavaScript file. Sometimes it's called the glue file if you're Googling for this stuff. So we're no longer going to be providing ourselves the import object. So instead of creating the import object ourselves and implementing the functionality, Emscripten is going to do this for us. And we'll look at this file in a bit. So now within our C++ code, we're going to add some rendering code, and then we're going to have a main now. So we have a main where we're going to initialize SDL, and you can see that what's happening is these SDL calls are not referencing the canvas, because in the generated files, they are assuming that there is a canvas here to draw to, right? So I'm initializing SDL. I'm creating a window and renderer that's 400 by 400. I'm initializing the TrueType fonts. I'm opening the font file. Yeah, and then at the bottom you can see the Emscripten set main loop is GameLoop. And what this is, what's happening here is, instead of our application taking up all the call time, we are saying that there's going to be a function called GameLoop, and this is the loop that you should call. So then Emscripten is calling this loop on every tick from the JavaScript side. So think of it as, instead of that we are running the loop infinitely, this function is going to be called once in a while, or basically as often as it can. Okay? Yeah. So now I port over the rendering code, which again, thankfully, is just a box. So in the first step, I do this. I only port over the square. I don't do anything with the text. So I'm just going to draw a red square on the side. Okay. So I port that code over. It looks something like, here's the mouse. Go into game logic. Where is the box here? So I have a rectangle. It has the X and Y size from the box that we're looping through. And I set the draw color to be red, and I call RenderFillRect. So this is the drawing of the box. So pretty simplistic. And that should work, right? So everything compiles when I do this. And initially, when I open it up, it looks like it should be. I run the code, I see the box, but then after a little bit, I get this error. It's saying that it cannot enlarge the memory arrays to a size of a certain amount of bytes. I either have to compile with initial memory higher than whatever the X is, or compile with allow memory growth 1. So either I have to say that initial memory within the sandbox is a certain amount, or the memory is allowed to grow. Okay? Straight above me. This is wonderful. I'm very happy for this. So wall number 4, the sandbox is an infinite. Up to this point, I've been using the default memory size, and it just has happened to fit. So everything that I've been using has just happened to fit into memory. Let me know if it's still too loud or not. It's still not clear to me on what level you can just recompile an external library to Awesome, or if you can use libraries that happen specifically. So everything external that you want to use has to be provided to you, or it has to be implemented and compiled to Awesome. So if you think of, there's one way to think about this. Not that one. If I close this, if we look at this, right? All of these functions that are here in the textual representation are my functions. So they are the only thing that is in this world. There is nothing else in this world except for these functions that are the ones that I wrote in the C++ side. And then there is this information here about what the environment looks like. Where's the stack pointer? What's the memory size? And then the external functions that are like provided from the outside. So the thing that you want to use either has to be implemented here somehow. You write them, someone writes them so they can be compiled here, or they are provided, right? So those are the only two options that you have, is that there's something externally that is providing you the Emscripten, no, not the Emscripten, the function that you need, or they are here, right? Those are the two options that you have. So for SDL2, a lot of it has been implemented and provided to you. And I can actually show you later on, we'll look at the bigger example later on, where I can show you where SDL2 is coming from, and then you can see better, like, if I want to use another library or something else, where does it have to live for me to be able to use it? Okay? I think that's kind of do and do, right? So this is the world. So if it's not here, we can't use it. Good. So the memory happened to fit, but we need now more memory since SDL has been involved. So I don't need to use all of these. I put all of them just to show you. I can set in the initial memory to some sort of amount of bytes. I can set the total memory to some sort of amount of bytes. And I can also say that the memory can grow after that. You can just use them as you fit. Okay. So this compiles and I can see the box. So I'm happy there. Now let's draw the text that should appear on the box. Okay. So that's wall number 5, file not found. So the next wall that we have is that in this environment, there isn't anything much else, like I showed in the example before. So the font file that I want to use doesn't exist. So it has to come from somewhere. So the idea of a file system as well is different from what we expect. We have to provide the files or embed them or somehow. So we have to basically show the sandbox environment where the files are or how the sandbox can access the files. So what I do in my build, so I have a folder called assets, which is one down from the build folder. And what I do is in the compile options, I say preload file. There's a folder called assets, and then I have the @ symbol. And what I'm saying is this folder assets is named /assets when you load it. So instead of doing ..assets when I'm loading it in the C++ side, I say /assets. So this is just saying that this is called this on the other side. And in the assets, I only have the TrueType font, but you can have all sorts of images and sounds and whatever. So yeah, so you can see here, when I initialize the TrueType font, I'm calling open font /assets and then the Arial bold and then the size. Okay. Also, what Emscripten can provide you is helper utilities to help with common development environments. So it has helper utility for CMake and make. So what you've been seeing is, so what I do em make clean, em make cmake ... and then em make. So why I'm doing the em make things in between is this is kind of the helper utilities, and then you call the command after that. So helper utility, the command, helper utility, command. That's kind of how that works. So now I have a CMake file. I say that the executable suffix is HTML. I give it the CPP files that I need, and now you actually see the commands that I've been using. So we can actually enable address sanitizer, which is where I got the memory issue from. We can do profiling. That's where we can, I'll show you that in a bit. Shell file is basically, because I don't want to use the default HTML file, I'm using an HTML file that I wrote myself. And I'll show you that one as well. The preload file is to get the file system. I can have optimization options. This is the same as before. Use SDL, the memory thing, and then I set those properties. So this is kind of a nice setup for when you're developing. Good. So now we have everything running. So let's look at that thing in action. So let's do the last live demo. So if I now go into, if I close this web server and go into the next folder, sorry for, let's build that. So now we have CMake outputs, as you can see. There we go. So now let's run this. We should get, yep. So now I have the game, and now this text and this information is being rendered on the C++ side. So now I can play the game in the same way. I also have this box below it for any console output that you want to use. The game is running the same. And now the extra tools that I have, so let's go into sources and go into the WASM, and I can show you, here we go, because we had a question there before. So now you can see that there's quite a difference between the initial section of the WASM file and what we had before. So now there's a lot more functions that are being provided externally. And what you see these functions are these are GL text image, so these are OpenGL functions. So Emscripten has implemented these OpenGL calls in JavaScript. So when someone is calling them from the C++ end, they don't exist there. So now they've been implemented in the JavaScript end, and this is the way to call them. Can you render via C++ just as you did, but use still a custom JS file to place the canvas? Yes. Yes, you can. So we're using the Emscripten HTML and JavaScript files out of convenience. If you want to do this yourself, you can. There's probably I think it's probably quite a lot of work, but you can look into those files, and I'll show you those files in a bit. But that's also why I showed you that I could have used a standalone WASM file and wrote my own the JavaScript and the environment and the imports to use for the random. but that's how that works. So I was technically providing the random functionality. I could have made it return 4 every time, and that would have been the implementation. Okay. So yeah, so you can see here that there's quite a few things. If I go to the bottom, I think as well, you have some sort of like operating system level. Like there's a sys call here. There's a like a long jump. So there's more stuff that is being provided than not just the graphics part of it. So it is quite a bit that you get. But there's also other cool things you can do here. So if I go into memory, for example, so this is just the JavaScript, not the JavaScript, the Chrome developer tools. I can actually click start here. I can play the game a little bit. La la la, having some fun here. And when I hit stop, I will get the memory allocations that are happening. So the most of them seems to be some Emscripten stack snapshot that's happening. So you can see if you're leaking memory, if you're allocating too much or too little, or what's causing the memory output that you have. There's also the really, really cool one, which is this one here. Let's refresh, because I want to start from the beginning. I started recording, and I'm going to play the game a little bit. Good stuff. Stop. It's going to load the profile from that. So now what we have is, this is called like the burn charts for the application. So now I can see, if I zoom in here, this is at 200 and something milliseconds. I have the calls that are happening, and also the SDL calls and how long they're taking. So here's the text thing, here's the render target. Here we're still in the JavaScript part of it. So I can see that the frame that I have is taking, well, how long is that? 3 milliseconds. So the task is taking 3 milliseconds. And another cool thing that's happening here is I can see a screenshot of, so here's the game being played. So if I zoom out, so here, so if I want to know what this frame, like, oh, this is the frame that I'm worried about, let's zoom into that one. Okay, here it is. So this is here's the frame. So I can look at like, oh, if this frame is having any problems, or why is this frame taking such a long time, etc., etc. Like, oh, it was some resizing of an internal buffer. Like, oh, okay, I need to figure out what's going on. And when I was developing this, here I have some paint output. Initially, I created the texture for the fonts every frame. So I would figure out like I need to draw the text too. I want to create a texture for it. The texture should look like this. And then I would do that every single frame. But the text for 2 looks the same every time. So I don't need to recreate it. So I made a cache of the textures. So now when I want to draw the text on the box, I go into the cache and figure out what's going on. So this was the chart before. So you can see it was pretty packed. And this is the chart afterwards. So I saw a problem, or I saw an optimization point. I could measure it before. Okay, we have a before point. I did the implementation. I measured it afterwards, and then there we have it. So I can see that, yes, it did have an impact. It had a positive impact. Okay, good. I can move on. So this is kind of the development flow that you have. So now, if we look into the code before, so we have the main here, and it's calling GameLoop. If we go into GameLoop, this is the classic delta updating. So we want to update every 16 milliseconds. So we only call the update function every 16 milliseconds. Update is it is higher up. Here it is. So for every box on the board, we call the update function, and the draw is here, where I create the screen texture. So I'm even rendering to texture. I set the background color, I clear the screen, I go through every box, I draw it. I set the render target just so I can copy the texture back over. and that destroyed the texture. So I'm actually creating a texture every screen, so I can see them there. And here's the cache that I had. So I'm just creating a texture and putting it into an array of textures. So that's a thing you can do as well. So just show an example of things that you do. And the logic is the same as before here. Okay. So if we go back to our slides. So now we see the game and the code in action. So let's summarize the walls that we encountered. So when you're developing, the files that you are using need to be served while developing. So you need some sort of web server that's hosting it. You can use emrun for that. All functionality that you depend upon, for example, the operating system level functionality, needs to be either implemented by you or given to you by the JavaScript end. Data needs to be primitives or needs to be converted in some way before you send it over to JavaScript, because they don't map to each other. Memory and size of the memory and how memory grows need to be thought about as well. So if you're using too much or too little, you can basically go out of bounds because you have a limited memory. And any files that you need to be embedded or preloaded with the output. Okay. One more thing, because I promised to show the JavaScript file. So I can show you here. So the HTML file that we have has regular just styling head. I have the canvas, and then we have a module. So this is the other way of importing. You can either create a module that's then used, or you can import it directly in, like I did before. So here's the key down things I was doing. And here's the thing with the module imports is that your functions will be named underscore something. So that's the difference between the import that I did before in the other example and this one. It's just called with an underscore before. So in the game.js, so this is now the generated JS file. So this is coming from Emscripten. So if we can actually look at, if I go, I just close that one. Let's find go to sources, awesome. Let's find one of these functions. So Emscripten GL bind vertex array. So this is some function that we should be able to then find it here. So this is then a function that is implemented on this side, and it's calling some bind vertex array in the GL context. So there's some open GL context, and it's calling it with the arguments. So every function that is used is provided. I think I can also find it then again. Yeah, it's twice, because you then need to map it to the name. This function is this name. So you can see, so this is what this file is doing. That this is, maybe you can think of this as your operating system, or this is your environment that you're using. So this ASM library argument is an object with all of the functions that you're using. And I think we can find that, yeah, when we have to create the ASM, we have this object called info, and here we have the env as before. So this is the environment that was that I showed you in the previous example. So if I look at this info, it's here in WebAssembly instantiate. So they don't use streaming, they use instantiate. Oh, there is an instantiate streaming as well. Yeah, okay, here it is. So they're doing the same thing. It's just being done for you. So yes. And if I go back here, go back to my slideshow, and I'll show you my last slide. This is me. Please look at the code. You can pull it, and there should be scripts for you to build it and run it. And yeah, if you have any questions. And while people are writing the questions, let's play a game, right? That's what this is about, right? Let's refresh. And we get a screen. So yeah, go down to merge here, Yeah, Kitty, hi. Am I doing a talk? Yeah, I'm doing a talk. The kitties have woken up. That was a bad move. Here, a question. Why would you use Wasm instead of JavaScript? The thing that's being run in the Wasm is more performant. Sorry. So that's the idea that this code here is being run in Chrome within a certain environment that is more performant than running the JavaScript. If you're not seeing a performance difference, like if this is not the very performance sensitive code, then yeah, use JavaScript. But if this is, like I showed earlier in the talk, there are people who were converting like DNA sequencing code over, and they saw a 20 times performance increase. Yeah. So performance, yeah. And what you can do is, like I mentioned earlier, is this is not necessarily just for games. If you have some bit of code that is performance sensitive or needs to be running very quickly, you can have a regular website with a regular JavaScript and everything is fine, except for that one function call, right? For this one specific function call, we need it to be very performant, and JavaScript isn't enough for some reason, right? You can write that in C++, generate a standalone Wasm, like I've been doing in the GameLogic example. Like this is just C++ logic. There isn't much else that's happening here. And then import that function over, and now you can call it like a JavaScript function. So you have your regular JavaScript and everything is happy, but for this one case, you call the optimized Wasm function, and there you go. That's pretty neat as well. Here we go, 64. That's a good one. Yes. Any more questions? I'll give you a couple of more minutes. You can play a game while that's happening. There's also there's a bug in the cache. It's a bug, not a bug. I don't know. I only cached the texture up to 2048. So if you go higher, it doesn't work. Is this really significantly more performant to use C++ for rendering instead of the GameLogic? Oh, no, not necessarily. I didn't do the performance difference to measure it. You can maybe look at that. But I don't know. I don't think the rendering part is that performant, or at least not in this case. If it's a more complex game, then yeah, I would imagine, especially if you use things like shaders, that's probably going to be a little trickier in JavaScript or might not be as performant. So if you have a 3D game and doing all of these cool 3D things, which you totally can do and people have done, then yeah, I think there is a performance benefit for having the rendering in JavaScript as well. Rendering in C++ as well. So yeah.